Hello, my name is John Hedengren and I'm an associate professor at Brigham University. I'm going to be talking today about teaching dynamics and control with an Arduino-based temperature control lab. An overview of some of the things I'll share are why automation is needed across industries. I'll talk about hands-on learning and some of the challenges with enrollment growth. Also an industry message to universities on skills and abilities that they need from students who are entering the workforce. I'll share a pocket-sized lab overview with teaching resource for learning objectives as part of the control course. And I'll give a MATLAB, Simulink, and also a MATLAB live script demo. And also talk about some of the community resources. So why is automation needed right now? Why is it so important? There are many industries that are being transformed by automation, and this includes medical automation where robots are performing surgeries, people transportation or product transportation with retail, and also one of the areas that I work in is the oil and gas industry, and there are many new topics such as data science, analytics, machine learning, cybersecurity, and digitalization. Now each of these have a very strong connection with process dynamics and control. It deals with the measurement and control of systems. Let's talk about engineering enrollment. So one of the things that we've seen from 2009 to 2018 is a very large increase in enrollment. And you can see some of the numbers here with freshmen, sophomores, juniors, and seniors. And I wondered why it was so much more for seniors, but I think that's because it's just taking longer for them to finish. So you can see freshmen coming in, maybe here. That should be reflected in the seniors number, but there are more. It might take 5 years for some of them to complete the degree. But even besides that fact, we've had a very large enrollment increase across the board, and this has caused larger classroom sizes and more resources needed to support these classes. So laboratory experiences like are found in many universities where they purchase a large piece of lab equipment, and then students schedule time to come in and use that lab equipment. Now that there are more students, it's really these lab scheduling is more challenging. All right, so maybe you have a new lab that you've designed and you have it hosted in one of your unit operations or laboratory workspace environments. Suppose that you have 16 students that are taking the class 10 years ago, but now there are 6 more. And so it becomes a problem with scheduling the time. Maybe you do groups of 2, and so each group of 2 has about 1/10 of the class time that they can use to go in and work with that piece of equipment. But then there's a new person in the class which might disrupt things a little bit. And so you've shifted to online learning. And so how do you still do the laboratory experience with this new scenario? Well, one of the things that we've done with this temperature control lab is made it accessible to students much like a textbook where all of the students in the class get one of these temperature control labs and then use it at home. And also it opens up the instruction to use this lab simultaneously during a class exercise. So for example, instead of saying take out your textbook and open to page 63, you could say take out your temperature control lab and let's do this experiment together. Some industry feedback was given a few years back where they said new emphasis is particularly needed on process safety, applied statistics, process dynamics, and applied process control through new teaching materials and effective integration into the curriculum. Now this is partially in response to some universities dropping the process dynamics and control course or integrating the controls course into courses like the unit operations lab. So we designed this new lab to really meet that challenge where you have a set point This is the PV, the process variable, and then you also have a controller output. So everything is contained within this one lab where they plug it in, hook it up to their computer, and then start working with modeling or control exercises. Now I'll describe a little bit more about how this lab was developed and some of the features of it, but basically here is your heater. I'll just say that's Q1, and here is your temperature measurement, T1, but there's another one next to it. There's Q2, and here's temperature 2 right here. Then there's also an LED that will turn on or off. So it's fairly simple in terms of the hardware, but very effective in terms of teaching the principles of process control. So it relies on an Arduino at its base. This microcontroller has different pins, and we hook up the temperature sensors to 2 different pins, analog inputs that read the voltage from those temperature sensors and then convert that into a signal that can then be transferred to the computer over a USB connection. All right, and then there's also ways to control the LED and also the 2 heaters. All right, so from the PC, computer, or Mac, or Linux, you can adjust the heaters and the LED, and also be able to measure continuously the temperature. One of the things that you need is to install the Arduino support package, and Mathworks makes it very easy to install that. So it's an add-on to MATLAB or Simulink, and you have 2 separate packages for those, whether you're working in MATLAB or Simulink. The packages will install all the needed firmware on the Arduino for the connection so that MATLAB or Simulink can read the pins and also write to the pins as well. So here's the hardware overview. We have that heater and temperature sensor that are placed next to each other. Here is the heater. This is a BJT transistor. We were originally going to use a power resistor, one that would be able to heat up or with applying more current, but we found that the switching mechanism, okay, so instead of using a MOSFET, we used a BJT transistor. This also heated up, so we just got rid of the power resistor and went with just this BJT. It works great as a heater. All right, and then we also have a temperature sensor. This is a TMP36 temperature sensor transistor, and it measures values between -40 degrees and 150 degrees Celsius. Now we limit the value to 100 degrees Celsius. So we have a default firmware that's installed on the device that will shut off if it reaches 100 degrees, but the heaters will rarely get above 70 degrees. Just the heater power supply is not powerful enough to get it much higher than that. So just from a safety standpoint, we have some protections built in so that students don't burn themselves. And then also we put some thermochromic paint on top of the heater so they turn pink when they get above body temperature. So above 37 degrees Celsius, they turn pink. So there's a visual indication of when they're hot as well. So these 2 transistors are then hooked up to some finned, so some things that help to remove the heat with the fins on the outside, some heat sinks, and then also this is attached right there, the temperature sensor, and you can see more details at this web address. So initially we had students that breadboarded these up themselves. We gave them all of the components, but there's a lot of possibilities to mix things up. Maybe they swap the cathode and the anode for the LED, or they misplaced one of these wires and then all of a sudden something heats up and stops working. And so we found that when we did this, about 50% of the labs didn't work. And so we switched over to a PCB printed and assembled version so that students could just use it out of the box. It was plug and play. And this gives a little bit of a timeline of some of the development. So initial version in 2014 and all the way to now where they are mass produced. 7,000 have been produced so far, but there's a lot of learning along the way. So when students attempted to breadboard these themselves, they made many mistakes, some melted parts, and overall a very frustrating experience for the students. And then we moved on to ones that we built for them, and we could do maybe about 10 of them, and then students would come in groups and use them. But again, that's much like the lab that we showed before, where they had to schedule time to come in and use them. They couldn't necessarily take them home. And then we switched over to mass producing them with the idea that students could take them home and work with them throughout the semester or in the classroom. And that's worked much better. And also has enabled us to distribute these to other universities as well. So some of the software that's commonly used in process dynamics and control is from a survey in 2015. And they showed that Excel and Mathworks software, Simulink and MATLAB, are some of the most popular. So this is from How We Teach Process Control from chemical engineers. And so we definitely wanted to create an interface that would be compatible with how a lot of instructors are using software within the process and dynamics course. One of the things that we found out, though, is that some students, even though they've had introductory programming courses or numerical methods courses, they still aren't entirely comfortable with programming, whether that's using Simulink or MATLAB or some other programming language. And so I created this 12 mini course, 12 module mini course. It can be completed in about 2 to 3 hours total. So about 15 minutes per module, just to give them a refresher on some of the material, but also for those that have never programmed before, it helps them get started. So it's taking them from maybe a frustrated state to one where they feel just a little bit more confident. All right, and then some of the topics that are used in process dynamics and control. There's certainly the feedback controllers and design and tuning, and then also PID controllers. But there are many other topics that are commonly covered. At least this is in chemical engineering, things like cascade control, or you have things like adaptive control, or state space, or other topics. So some of them are more common than others. We certainly wanted to create lab modules that would cover many of the most common ones and have an exercise that would go along with each of these topics, so that when instructors are using this lab, they can be able to adopt one of those very easily, put it into their course, and maybe that complements some of the theory or math that goes along with the course. So this is an overview flowchart of how I teach the process dynamics and control course. We start with controller design. So just thinking about set point, output, and PV, and how you would select those to get a system that can be controlled. And then we look at whether data is available. If it's not available, then we develop physics-based models, such as from mass or energy balances. But if we do have data available, or a simulator of that, we can then take a different route and do things like a step test, okay, or we can do a doublet test, PRBS, pseudo-random binary signal, or even use historical data and harvest that to come up with models. So with physics-based models, sometimes you need to linearize the model to get it back into a first order plus dead time form. If you're doing a graphical fit with a step test, then that gives us a first order or second order model, or with regression, coming up with time series or state space models, or even physics-based empirical models. So that's the end of the first part of the course. This is more on the modeling. Develop a model of your process. And then once you have a model, then you can do interesting things like develop tuning correlations, and this is the second part of the course. So this was the modeling up here, and then they look to see if they have measured disturbances. If they do, then they might include a feed forward or a cascade control architecture. And then if not, they look to see if it's an integrating system. If it is, then I have them design a P-only controller. If not, then a PI or PID controller. And then from there, go to stability analysis using methods like route array, Bode plots, root locus plots, and others. And then once you have the limits of the gain for the controller, then going on to tuning correlations like ITIE or IMC, internal model control. Okay, and then looking at control performance, and then tuning. Okay, so tuning the controller, and then finally monitoring the performance. So that's the overall architecture of the course. And at every step I give a homework assignment and also a lab exercise that goes along with that homework assignment. So this is the basic interface in MATLAB. Students connect to the lab. This creates a new connection, so now you can send and receive signals. Once they've plugged it into their computer, then they've run this command in MATLAB. Now they have a new lab object they can use to send and receive signals. So for them to turn on the LED, they send this command to turn it on to 80%. And then it illuminates and flashes the LED. To read the temperature, they use this, lab.t1. So lab is the object, and then t1 is the method that goes out and gets the next temperature in degrees Celsius and then displays that at the terminal. And the final command here is this lab.q1. That's turning on the heater to 50%. So if the heater, you wanted to do a step test, or student wanted to do that, go from 0 to 50% and observe. Okay, so that might be like this. And then they would observe the temperature response. Okay, and then from that they could get a gain and a time constant. Okay, so there's the delta y, there's the delta u, and so their gain is going to be equal to delta y over delta u. And then they can get a time constant, how long it took to get 63% of the way there. And so there's their tau p, and then maybe their dead time as well. Okay, so they use graphical fitting, they use regression, and other methods. Once they have these very simple programming methods, they can program these in MATLAB or in Simulink. So I'll show examples of both of those. There's also 2 heaters and 2 temperature sensors, and so later on they'll do interacting control, cascade control. It gives the ability to put a disturbance, maybe you turn on this heater, and that provides a disturbance for the other controller. Alright, so many different things you can do with multi-input, multi-output, or single input, single output, or different control architectures with this lab. Okay, and again, the new commands here are just for temperature 2 or the heater 2. In this case, the heater 2 is just off. Alright, so I'm going to show the Simulink interface. This shows the different pins and just a really brief overview of how students program that up from scratch. So they open up a new model and insert all of those elements, and then they can run it. Okay, so it gives them a slider bar right here. They can adjust the heater it starts at 0, but they could set it to 50%. And so there's the 50% on the Q1. And then what they want to do is look at the temperature one and the response. So there's the plot right here that gives them the temperature one. All right, and this is just going to show a demonstration of doing this. I'm going to turn on the heater to 53%. All right, and you'll see over here, you'll see temperature 1 and temperature 2. So you'll see temperature 1 is the yellow. That one's going to increase. And temperature 2 will also increase later. Right now they're both a little bit hot, about 26 degrees. I just finished another test, so temperature 2 is still going down. It's still cooling. But then you'll see it start to come up again as it starts feeling the heat from temperature 1. Now, one of the things that you'll see with this is you saw a little spike down right here. Now, this is real data, and it's really good for students to see real data that isn't necessarily all the way clean all the time. There's some noise. There's some voltage variation just from some of the interference from lights or cell phones or other things that are going on. And so it will be very much be real. And so I have different steps here. You can see that I turned off the heater about right here, but it continued to rise in temperature. So that always intrigues students. Why did the temperature continue to rise even if the heater was shut off? And then I set it to different levels. You could also plot the heater values here if you wanted to be able to show those. You could put the steps there and show those along with the temperature. So you can see temperature 2 is starting to rise here as it starts feeling some of the convective heat from temperature 1. Okay, and so these are just some steps that I'm performing. You can do doublet tests or other types of steps with this in manual control. Okay, the next one I'm going to show is how to then take this manual control and now create an automatic control mode with PID. So go ahead and eliminate these first sliders here. I'll just leave heater 2 at a value of 0. We could change that later if we wanted to throw in a disturbance. But now this slider or this input is going to become my set point. So that's going to be my temperature 1 set point now instead of my heater that's going into this block. So this is how I control the TCLab right here. You can see the Q1 and the Q2 coming in, and then T1 and T2 going out. I'm going to have 3 scopes here. I'm going to have temperature 1 going to the second scope, and I'll have the set point going to the first one, just so I can see the set point and the PV on the same plot. Okay, I'll throw in a PID controller just from the library of models, and I also need a summation to be able to compare the set point with the PV. So here I have my signs I need to adjust. So I have positive and negative sign, and those arrows are automatically connected for me. Now I'm going to right click and bring this over to the negative terminal, and then go ahead and right click off of this to bring another signal off, and that will show me my Q value. And then the final thing that I need is my set point. Alright, so here comes my set point, and okay, I'll just rearrange some of the lines. So now I have set point, PV, and OP coming into that scope. So I can look at them all together. Okay, now what I'm going to do is I'm going to put in a proportional, integral, and derivative. Okay, and this came from the step response where I came up with some kind of default, and then I'll put in the upper and lower limits of saturation. On my heater value, I can't go below 0 or above 100, and put in some anti-reset windup with back calculation. Alright, I'll click OK, and now I have my feedback control set up. and I can run this, and this will be a 5-minute test, 300 seconds. Alright, so it's going to compile and then it'll start going. I'll go ahead and open up this scope to be able to look at the PV, OP, and set point. So these are all things that students can do, build their controller from scratch, with a couple instructions, or sometimes I just give them the initial version and then have them do things like, put in the PID controller and tune it. Alright, I'll adjust this just so we can see the model and also the scope on the same screen. Alright, so from here you can see this is the measured temperature. Down below, that's my set point and also the OP. Alright, so it's initially 0, and then this is starting at about 21 degrees Celsius right up here. Okay, so there I have these values. Okay, now I'm going to change my set point to 50 and then just rescale this plot. And so you can see the new set point right here. And then this up here is my PV. It's a little bit hard to see, but and then you're going to see also, oh sorry, that's the output up here. That's the heater output, and this is my PV. So I have my PV, OP, and set point. And we're going to see the PV get closer to the set point. You can see the output already starting to drop as the proportional term of the PID controller, the PI controller is, the error is getting less. And so students are watching. This is a real time, and so you can see the approximate time constant. It's about 1 to 2 minutes for the time constant. So not too slow, so it takes a long time to run these, but also not too fast. So students can observe the dynamics. They get a feel for some of this inertia that's happening as you put in more heat. It takes a while for the convection, the conduction to transfer. And so this is a fairly sluggish controller, and you're going to see the PV start to level out here, and it'll eventually climb and come back up to the set point, but maybe the student is saying, hey, this is too sluggish at this point, so they want to go in and maybe adjust the PID controller, and you can see a couple scopes here as well. They're looking at some of the values. Okay, so they can go in as this is running and maybe adjust the integral or the proportional part of this. So we can change it from 10 to 15, make it a little bit more aggressive. All right, and then we'll see immediately the heater jumps back up, and it's going to then approach the set point just a little bit faster. Alright, so this creates an interactive PID controller students can work with. They're looking at the PVOP and set point and making tuning corrections based on what they observe. And students, if they have too aggressive of a controller, they will get overshoot and oscillation, and it won't go unstable, but they will see more oscillation. They can also see things like, kind of quantized levels here, okay, discrete levels of their temperature measurement that causes the proportional term to, come down in kind of discrete steps. And so that's very good for students to see, that you don't have infinite precision. It's a, I think it's a 12 or 10-bit signal that's coming from the analog. So all these are just real characteristics of the signal that you see in a real controller. All right, I'm going to go on to this next one, which is a live script. And this is a kind of a newer thing from Mathworks. They introduced a couple years back. It's a very interactive. You could see, some equations in there with the equation editor. It looks very nice. We're adjusting the tuning constants and then observing the response in simulation. And then as a next activity, we'll go on and implement our best tuning parameters. So once students have worked with this, kind of come up with what they want in terms of the response, then they can also, as a next step, then implement those and run the TCLab directly from this live script. So here are the numbers that we're inputting. All right, and then run it, and you can see the calculated, which is in the red, and then the purple right here that's kind of going over it as you see it come along. Those are the measured values. So students are able to compare predicted versus measured values, and you can see there's just a little bit of a difference right here, but overall it's fairly close to what actually happens in practice. So again, this is very motivating for students that they can predict something will happen, and then they test it to verify their tuning gave approximately the same values. All right, so there are lab exercises, as I mentioned, for every point of the course, and many of the major topics that are taught by most faculty. So for example, step tests. We have some mathematical modeling based on energy balances like convective or radiative heat transfer. So especially for mechanical or chemical engineers, heat transfer courses are often taken before the process dynamics and control course, so shouldn't be too unfamiliar to students. We have them linearize this model. Okay, there's a temperature to the fourth in the radiative heat transfer term. So they linearize this to come up with a first order model. We also have other exercises like a graphical fit. So they do a step response, and then they fit the gain and the time constant and any dead time. Then they also use regression. So they use computer optimization to fit their model. So you don't necessarily have to have just one step. You know, they can have multiple steps in their step response. Look at controller design as well, just how the signals are placed and the actuators, how those all fit together to create the controller. We look at P-only control, PI control, and PID control. Just noticing on P-only that there's offset. With non-integrating systems and P-only control, it leads to offset. So things like that they can verify, they can calculate, and then verify that it has a certain amount of offset. Also, other exercises as well. This is 11 through 16. There are 22 total that I've prepared, but other instructors have also prepared exercises. Here's how to tune a PI controller, tuning a PID, looking at feed-forward control. So this extra temperature 2, is used as a disturbance variable. So when we are able to measure that, we're able to anticipate what's going to happen to T1 and make proactive moves on that. Looking at control actuators and sensors, impulse response, and then we go on to other topics as well. So one of the other topics I cover later in the course, kind of as an add-on, but I also have another course on this, is advanced control and optimization. So we look at model predictive control. And I talked to them about PID control being a feedback control. So it would be like driving a car while you're always only looking backwards. So you're always looking at measurements in the past. Versus model predictive control, you're able to use a model at the current time and look into the future to predict what's going to happen with your sequence of moves, okay, and how that's going to affect where you're going, but also future constraints or preventing things like overshoot. So we introduce this to students as well, in addition to the PID topics. It's more of an advanced topic, not as good for undergraduate course, but I give them just a sample of what to look forward to with the graduate level course. and then we run some tests. This is a model predictive controller. You can see temperature 2 here and temperature 1, and then it's coordinating the moves and the move plan for Q1 and Q2. So we use this for model predictive control. Here's the future control horizon that it shows with the predicted move plan. So I'll just share that with you one more time. Okay, showing the future move plan where it's anticipating that the system will go. Okay, with different set point changes along the way, and you can see, here it's there's the move plan, and then what was actually done. You can see that after the bar. We also have students learn about things like moving horizon estimation. This is in the advanced control course, where the model is not fit beforehand, but when the controller starts, you start collecting data, start to fit the model as you go in this purple region right here. That's where the horizon for the model fitting is occurring. Okay, and you can see that's a shifting horizon. That's what we call it, a moving horizon estimation. And then beyond that, we use the same model for predictive control. And so this shows this in an interactive way. Students run it and come up with different model forms they can fit in. Okay, here's one other thing that I use it for as well, is in teaching machine learning. So there are many different machine learning methods. There are classification methods, clustering, and dimensionality reduction, but also regression. And I'll just share an example of how I use the Temperature Control Lab in teaching about classification and different methods that are available. So you can see in this chart, you have things like naive Bayes, k-nearest neighbors, okay, support vector classifiers, or others. And so these are some of them that I teach. Okay, we have the supervised learning methods and then the unsupervised learning methods. And what I'll share here is, I'll go ahead and just start this and then talk about it. We measure the temperature up here and also calculate features. These are the temperature derivatives with respect to time, the first and second derivatives of temperature with respect to time. And then from that we get the heaters on or off. That's our labeled data. That's right here at the top. That's Q1, and that is either 0 or 100%. Now at the beginning we use the features that are above and the Q1 value to train these classifiers. So they're trying to learn when the heater is on or off using, in these cases, labeled data. And at a certain point, we have it start predicting whether the heater is on or off without actually knowing if it is or not. So we can see the heater turning on or off and all of our predictions there from the different classifiers, both from the supervised learning methods and the unsupervised learning methods. So this data gives them real-time and gives them their own data set. So they're not just downloading something from Kaggle, but they're generating their own data, doing machine learning with this lab. All right, so this is my course overview, and I've mentioned these 22 lab modules that cover physics-based modeling, empirical modeling, parameter regression, PID control, and tuning, and also some of these advanced control or machine learning modules as well. But one of the things I've noticed in all of the instructors that are using this lab now is that they also have been developing their own labs and inserting the lab experiences at different points in their courses. And so I've appreciated that perspective because everybody has a different way of teaching the course, and more than anything I hope this lab is a resource to be able to take what's there and modify and adapt it to the way that you like to teach the course. If you'd like to receive a temperature control lab, I have a limited number of these that are available for instructor evaluation. So please send me an email at the address that I've indicated there. Just include your name, shipping address, and course information. And I'd love to hear about your course and how you teach it. It'll typically arrive in 2 to 3 business days in the U.S. or 6 to 20 business days international. And also, when students want to get one of these, they can just get it from Amazon. So it's much like saying that you're going to use a textbook for a course. You can have a personal copy, but then you just ask students to get one of their own for the exercises in the course. So this is a community initiative. There are many learning modules, and here's the address that you can go to download some of the instructor resources. There's also the URL that's printed on the TCLab itself that gives many more resources. Many have contributed to this temperature control lab with language translations or modeling and control modules. And also there are new microcontroller labs that are under development. I've appreciated all of the universities that have adopted this lab, many instructors that I've heard from, and from the best I can tell, it's about 70 universities that are using this. Some of them it's the professor who's using it just to demonstrate things in class, and in others it's where students all have an individual copy of the lab. I'd also like to thank the many collaborators that have enabled this community resource. Melda and Samveeth at Mathworks, who have helped with some of the software interface and providing resources for MATLAB and Simulink. Also, Abe, Junho, Joshua, and Nathaniel at BYU for developing the lab, but also developing resources for students to use it. And then Jeff Cantor and Carl Sandrick for developing additional software and instructional resources. And then Paolo and Anthony Roast here, they've helped to develop some of the pedagogical studies with the Temperature Control Lab to show its effectiveness with students and in the classroom. So I appreciate them for their work. And here's some of the articles that and conference publications that have come out in the last 2 years with the Temperature Control Lab. One of the interesting things in addition to education is there are a couple publications where the Temperature Control Lab is used as a benchmark to test new control or optimization methods. I'm so excited about that possibility as well. There are many simulation standard models, but very few hardware devices that are used as standards to test new methods when they come out. All right, and with that, I'd be glad to take any questions.